Far beyond the planets, Voyager 1 is still moving outward. Its radio signal reaches Earth only after crossing an immense distance, taking many hours to arrive. By the time engineers receive a message from the spacecraft, Voyager is already farther away than it was when that message began its journey. Voyager has traveled beyond the region dominated by the solar wind and into interstellar space. It will never return to the planets. Its path continues outward, carrying it farther from the Sun with every passing year. But Voyager is not leaving the Milky Way. That difference is the beginning of our journey tonight. The galaxy is usually pictured as a bright spiral of stars. From a distance, we imagine a thin, luminous disk crossed by dark lanes of dust with a brighter concentration near the center. It looks like an object with a shape and therefore perhaps with an edge. But the bright disk is not the whole Milky Way. Beyond the bright disk lies a much larger gravitational structure, extending far into regions where very little visible light remains. Most of the mass responsible for that gravity does not shine at all. So leaving the galaxy is not simply a matter of traveling beyond its last bright spiral arm. It is a question of whether that spacecraft ever has enough energy to stop belonging to the Milky Way gravitationally. The Sun itself is moving rapidly through space, carrying Earth and the rest of the solar system around the galactic center. Voyager shares much of that motion. So does almost every nearby star. That makes the word escape more subtle than it first appears. A traveler can move outward for a very long time and still remain bound. So tonight we will follow the idea of escape outward, one layer at a time. We will begin close to the Sun, where Voyager gives us a familiar scale. We will look at what escape velocity really means and why the fastest spacecraft is not necessarily the one closest to escaping. Later, we will meet stars that nature itself has thrown outward at extraordinary speeds, and beyond the visible disk, we will reach the quietest and most important part of the story, the enormous unseen halo whose gravity makes the Milky Way far larger than its familiar spiral of light. You do not need to hold every distance or speed in mind. We are following one question outward, not where the Milky Way stops shining, but where an object finally stops belonging to it. The first step is to locate ourselves inside the system we are trying to leave. The Sun is not near the center of the Milky Way. It lies roughly 26,000 light years from the galactic center, embedded in a comparatively modest region of the disk, sometimes called the Orion Spur. From here, the galaxy does not look like a spiral at all. We are inside it. On a dark night, the Milky Way appears instead as a pale band crossing the sky, made from the combined light of distant stars, seen through the thickness of the disk. The familiar spiral shape comes from observations gathered across many wavelengths, and from mapping the positions and motions of stars and gas from within. That stellar disk spans roughly 100,000 light years from side to side. Near the Sun, neighboring systems are usually separated by several light years. A spacecraft traveling through this region would spend almost all of its time crossing empty space. The galaxy is mostly empty volume, and yet we remain securely inside it. The reason becomes clearer when we stop thinking about the Milky Way as a collection of objects and begin thinking about it as a gravitational system. The Sun is moving around the galactic center at a speed of a few hundred kilometers per second. Earth moves with it. So do Voyager, the nearby stars, and almost everything else in our part of the disk. One complete circuit takes roughly 250 million years. Since the Sun formed about 4.5 billion years ago, it has completed only roughly 20 of these enormous galactic orbits. The gravity shaping that motion comes partly from stars like the Sun, partly from clouds of gas and dust, and partly from a much larger reservoir of mass that we cannot see directly. What matters first is that gravity does not need the space between stars to be crowded. A star several light years away barely interacts with us in any everyday sense, but add the gravitational influence of billions of stars, the central regions of the galaxy, interstellar matter, and the unseen mass surrounding the disk, and together they create a potential deep enough to keep the solar system moving on its galactic path. This is why an outward journey can be deceptive. A spacecraft may travel farther and farther from the Sun, while still sharing the Sun's broader orbit through the Milky Way. And none of those milestones by themselves mean it has escaped the galaxy. The obstacle is not a line waiting somewhere ahead. It is the accumulated gravity of the system, behind, around, and far beyond the traveler. So once the solar system is placed inside its larger orbit, the problem changes. Distance alone can no longer tell us whether something has escaped. We need to know how much motion is enough for gravity, however long it keeps pulling, to never bring the traveler back. Escape velocity is often described as though it were a speed limit printed on the side of a gravitational system. The real idea is gentler and a little more useful. Escape is about energy. Imagine throwing a small object upward from Earth. As it rises, gravity slows it. If it begins too slowly, it eventually stops climbing and falls back. Give it more speed, and it travels farther before returning. At one particular threshold, the object has enough energy that gravity can keep slowing it forever without ever reversing its motion. That is escape. The object simply changes from a trajectory that must eventually return to one that does not. The same principle applies to the Milky Way, although the gravitational landscape is far more complicated than the one around a single planet. Near the Sun, modern estimates place the galactic escape speed scale at roughly 500 kilometers per second, with meaningful uncertainty depending on how the galaxy's mass is modeled. It does not mean that any object seen moving at 500 kilometers per second has automatically escaped. Speed has to be measured in the correct reference frame. Voyager 1, for example, is often described as moving outward from the Sun at about 17 kilometers per second. That number tells us something important about its departure from the solar system. But Voyager and the Sun are themselves already moving together around the Milky Way. So comparing Voyager's heliocentric speed directly with the galaxy's escape speed mixes two different measurements. To ask whether an object is bound to the Milky Way, astronomers need its full motion relative to the galaxy itself. Much of the Sun's motion carries it sideways around the galactic center rather than outward from it. That sideways motion is not wasted. It is what keeps the Sun in orbit. The Sun has enough motion to avoid falling inward, but not enough total energy to leave the galactic gravitational system behind. Our solar system is already moving through the galaxy at a few hundred kilometers per second, yet it remains securely bound. A high speed by itself does not tell us whether something is escaping. We also need to know where it is, which direction it is moving, and how deeply it sits inside the galaxy's gravitational potential. If the Milky Way contained only the stars and gas we can see, its gravitational pull would weaken with distance in a relatively straightforward way. Far enough from the bright disk, escape should become much easier. But observations do not show gravity fading that quickly. Stars far from the galactic center continue moving as though far more mass is present than the luminous disk can account for. The threshold for escape is telling us something about the galaxy itself. The farther we follow this question, the less it becomes a story about engines. It becomes a way of weighing the Milky Way. Voyager 1 is often the first spacecraft people think of when they imagine leaving the solar system. After launching in 1977, Voyager used close encounters with Jupiter and Saturn to reshape its trajectory and gain enough energy to continue away from the Sun. It no longer loops back toward the planets. Its course carries it steadily into interstellar space. That makes Voyager an escaping spacecraft in one important sense. But it is not the fastest spacecraft humanity has built. That record belongs to Parker's solar probe. During its closest passages around the Sun, Parker has moved at roughly 190 kilometers per second, many times faster than Voyager's outward speed relative to the Sun. Parker becomes so fast because it falls deep into the Sun's gravitational field. As it approaches the Sun, gravitational potential energy is converted into motion. The spacecraft accelerates, sweeps through perihelion at remarkable speed, and then begins climbing outward again. But it remains on an orbit that brings it back. Its speed is part of a bound trajectory. Voyager, moving much more slowly, is following a path that does not return to the Sun. What matters is the object's total energy within the gravitational system being considered. Chemical rockets provide strong thrust for a short time. They are excellent for lifting spacecraft from Earth and placing them onto carefully chosen trajectories. Planetary gravity assists can then alter those trajectories without requiring the spacecraft to carry enough fuel for every change in speed. Voyager's own journey depended on this technique. A close passage near a moving planet allows a spacecraft to exchange a tiny amount of momentum with that planet. The planet's motion is essentially unchanged, while the spacecraft can leave the encounter on a faster or differently directed path around the Sun. But a gravity assist does not create unlimited energy. A sufficiently energetic probe could, in principle, be placed on an unbound galactic trajectory. The difficulty is practical. Accelerating a spacecraft to hundreds of kilometers per second while carrying useful instruments, power systems, communications equipment, shielding, and perhaps one day much greater payloads, demands enormous amounts of energy. And even if that speed could be reached, the galaxy would still take a very long time to cross. So, human engineering gives us an important boundary, but not the final answer. For that, we need to leave spacecraft behind and look toward the center of the Milky Way, where a small number of stars have been accelerated to speeds that make every human-built probe seem slow. One of those stars gives us the clearest natural example of what galactic escape can actually look like. Near the center of the Milky Way, gravity operates on a scale very different from anything around the Sun. At the heart of the galaxy lies Sagittarius A star, the supermassive black hole with a mass of about 4 million suns. From a great distance, its gravity behaves like the gravity of any other object with the same mass. It does not pull stars inward like a vacuum cleaner. Most stars near the galactic center simply orbit within the combined gravitational field around them. But a very close encounter can produce a different outcome. Imagine two stars orbiting each other as a binary system for most of their lives. Each star follows the other around a shared center of mass. Their motion is stable because their mutual gravity keeps the pair together. If that binary passes close enough to the central black hole, however, the enormous difference in gravitational pull across the system can separate the two stars. One may be captured into a tighter orbit near the black hole. The other can leave the encounter carrying away an extraordinary amount of orbital energy. This process is known as the Hill's mechanism. It turns a pair of ordinary orbiting stars into two very different travelers. One remains behind. The other can be thrown across the galaxy. Astronomers call stars moving at these extreme speeds hypervelocity stars, and one particularly useful example is known as S5HVS1. Its measured motion corresponds to roughly 1,750 kilometers per second in the galactic frame. That is not merely fast compared with spacecraft. It is fast enough for the star to be gravitationally unbound from the Milky Way under current models of the galaxy's mass. The important evidence comes not only from the speed itself. Astronomers can measure where the star is, how quickly it is moving, across the sky, and how its light shifts along our line of sight. With those components combined, its trajectory can be reconstructed backward through the gravitational field of the galaxy. For S5HVS1, that reconstructed path leads back toward the galactic center. The best fit journey places its ejection there roughly 5 million years ago. That reconstruction became possible through extremely precise stellar measurements, including astrometry from the European Space Agency's Gaia mission. Gaia was built to map the positions and motions of enormous numbers of stars. S5HVS1 is therefore more than an unusually fast star. It gives us a natural demonstration of galactic escape. Human spacecraft have not approached this kind of unbound trajectory. Nature can create one by rearranging gravitational energy during a close encounter in one of the deepest parts of the Milky Way's potential. Other mechanisms can also produce fast runaway stars. A star in a binary system may be released when its companion explodes, for example, and some high-speed stars have origins elsewhere in the galactic disk, so not every rapidly moving star points back to Sagittarius A star. Each candidate has to be measured carefully. Its full three-dimensional motion matters, its origin matters, and the galaxy's own gravitational model matters. But S5HVS1 gives us something unusually clear. Here is a star whose motion is fast enough that, according to our present understanding of the Milky Way, gravity will not eventually bring it back. That resolves one part of our question. Escape from the galaxy is physically possible, but it also changes the question. Until now, we have been asking how fast an object must move. The star shows us that speed can provide an answer. What it does not tell us by itself is how large the thing being escaped actually is. A star can leave the bright, spiral disk behind and still spend millions of years traveling through regions shaped by the Milky Way's gravity. So from this point onward, the speed is no longer the most interesting part of the journey. The mass doing the pulling is, and to understand that mass, we have to travel beyond the familiar disk of stars. From the sun's position, the bright stellar disk still fills much of our idea of what the Milky Way is. But if a traveler continued outward, the character of the galaxy would begin to change long before its gravity disappeared. The spiral arms would grow thinner. Bright star-forming regions would become less common. The familiar concentration of stars would gradually give way to a much sparser population. There would be no moment when the light suddenly stopped. The disk has no sharp rim. Its density simply falls. Between those stars lies the interstellar medium, thin gas, dust, magnetic fields and energetic particles spread through enormous volumes of space. By terrestrial standards, this material is extraordinarily sparse. A spacecraft moving through it would not experience anything like wind or fog. Most of the journey would still feel like travel through vacuum. So again, the difficulty is not that something blocks the way. The deeper obstacle remains gravitational. Far beyond the main disk, stars still exist, but they are arranged very differently. Instead of following the flattened spiral structure, many belong to a much more diffuse region called the stellar halo. This halo surrounds the disk in a roughly spherical distribution. Its stars are generally old. Many contain smaller proportions of elements heavier than hydrogen and helium than stars such as the Sun, a chemical clue that they formed early in the history of the galaxy. Others appear to have arrived later from smaller galaxies absorbed by the Milky Way. That history is still visible. Long streams of stars stretch across the halo, the remains of smaller systems pulled apart by galactic tides. A dwarf galaxy can lose stars over repeated passages until its former shape disappears, leaving only a faint ribbon of motion wrapped around the Milky Way. Globular clusters provide another set of landmarks. These compact collections can hold hundreds of thousands of stars, sometimes more, packed into regions only a small fraction of the size of the galactic disk. Many orbit far above or below the plane where the Sun resides. Some are almost as old as the Milky Way itself. Together, the streams, clusters, and ancient halo stars show that the galaxy extends beyond the bright spiral we usually picture. They also reveal how the Milky Way grew. Its history is not only the history of stars forming quietly inside a disk. It is also the history of smaller systems being drawn in, stretched apart, and added to a larger gravitational structure. For our outward traveler, however, these visible objects would become increasingly rare. There would eventually be fewer and fewer stars nearby to mark the journey. The Milky Way would begin to look less like a place filled with luminous objects, and more like a gravitational field containing only scattered points of light. And this creates an important clue. If the visible matter were almost gone, gravity should weaken dramatically. Yet measurements of stellar motion and the behavior of distant traces show that the galaxy continues to exert more gravitational influence than the visible stars and gas alone can explain. By now, the bright disk is behind us. The stellar halo is becoming sparse, but the Milky Way is not. The farther we travel, the less of the galaxy we can see, and the more of its gravity remains to be explained. That missing explanation is the next layer of the journey. It is also the reason the true Milky Way is far larger than its light. By the time the visible stars have thinned into the halo, the Milky Way has become difficult to define by light alone. Gravity gives a different answer. One of the clearest clues emerged from measurements of how stars and gas move around spiral galaxies. If most of a galaxy's mass were concentrated, where most of its visible light is concentrated, then material orbiting far from the center should move more slowly. The logic is familiar from the solar system. Mercury moves around the Sun much faster than Neptune, because Mercury is much closer to the mass, doing most of the pulling. A galaxy is more complicated than a star with planets around it, but the same basic expectation remains. Far enough from the bright center and disk, orbital speeds should decline. In the 20th century, astronomers began measuring those speeds with increasing precision. The work of Vera Rubin and Kent Ford became especially important. Using spectra of spiral galaxies, they tracked the motion of stars and glowing gas at different distances from galactic centers. The outer regions were not slowing down in the expected way. Instead, rotation speeds tended to remain roughly flat. Something was providing additional gravity. And whatever it was not appearing in the visible light. This did not mean that every detail was understood immediately. Astronomers had to consider the distribution of ordinary matter, the uncertainties in distance, and the way galaxies are structured. But as measurements improved, the general pattern persisted. The visible stars and gas were not enough. The simplest explanation was that galaxies are embedded in much larger reservoirs of unseen mass. We call that mass dark matter. The name can sound more mysterious than the evidence itself. Dark matter is called dark because it has not been observed to emit, absorb, or scatter light in a way that would make it directly visible to telescopes. Its existence is inferred from gravity. That inference does not rest on rotation curves alone. Light provides another route. According to general relativity, mass changes the geometry through which light travels. When light from a distant galaxy passes near a massive foreground object, its path can be bent. The effect is called gravitational lensing. Sometimes the distortion is obvious. A background galaxy can appear stretched into an arc or repeated into multiple images. More often, the change is tiny and only becomes useful when astronomers measure the shapes of many galaxies together. Either way, the amount of bending reveals how much mass lies along the path. And once again, the mass inferred from gravity exceeds the mass that can be accounted for by stars and glowing gas. Different observations, using different physical effects, point toward the same broad conclusion. The Milky Way is therefore not merely a luminous disk surrounded by a few old stars. It sits inside a much larger gravitational halo dominated by dark matter. Most of that halo cannot be photographed. There is no telescope image in which its outer boundary glows faintly into view. Instead, astronomers map it indirectly through the motions of stars, globular clusters, satellite galaxies, and stellar streams, asking what distribution of mass best explains the paths those objects follow. This is also why estimates of the Milky Way's total mass remain less exact than the mass of something like the Sun. We are measuring a system from inside it. Its outer regions contain fewer bright tracers, and much of the mass we are trying to map does not interact with our instruments through light at all. A useful scale is that the Milky Way contains total mass of roughly 1 trillion suns, though the exact value depends on the model and the observations used. Most of that mass is not in the stars, and this is the quiet reversal at the heart of our journey. At the beginning, the galaxy seemed to be the spiral of light across the night sky. Farther out, that light became sparse. Yet the galaxy did not disappear with it. In a gravitational sense, much of the Milky Way was never visible in the first place. The farther we traveled, the less we could see, and the more clearly the unseen structure revealed itself through motion. So the true edge we have been looking for cannot simply be the last star. It cannot be the last globular cluster, and it cannot be a faint line surrounding the spiral arms. To find out what an edge means here, we have to replace the idea of a border with something more precise, the point at which a traveler is no longer gravitationally bound to return. The word edge suggests a place, a shoreline, a boundary where one region ends and another begins. The Milky Way does not offer anything quite so simple. Its visible disk fades gradually. Its stellar halo becomes increasingly sparse. Its dark matter halo is inferred through gravity rather than traced by a glowing surface. And gravity itself does not suddenly switch off at a particular distance. It weakens. That means the true question is not where the galaxy physically ends. It is whether a traveler remains bound to it. For a planet orbiting a star, that distinction is straightforward enough to calculate because most of the mass is concentrated near the center. For the Milky Way, the calculation depends on how mass is distributed across an enormous volume, including the dark matter halo. That distribution is still being measured. Astronomers estimate the galaxy's total mass by following objects that respond to its gravity. Some of those objects are stars far from the disk. Others are globular clusters or streams of stars left behind by disrupted dwarf galaxies. Satellite galaxies provide another set of tracers, moving at distances where the visible Milky Way has already become a relatively small part of the scene. Each trajectory adds a constraint. If a distant object is moving quickly but remains gravitationally bound, the galaxy must contain enough mass to hold it. If its motion is difficult to reproduce under one halo model, the model can be adjusted and tested against other tracers. The result is not one perfectly measured radius. Different studies can arrive at different estimates for the Milky Way's mass and for the characteristic size of its halo. Part of the disagreement comes from the limited number of reliable tracers in the outermost regions. Part comes from the fact that a dark matter halo does not need to end sharply. Its density may simply continue declining until distinguishing the Milky Way's contribution from the surrounding environment becomes increasingly dependent on definition. So when astronomers describe a halo radius, they often choose a physically useful convention. One common approach defines a region within which the average density reaches a particular threshold, compared with the larger cosmic background. That gives researchers a practical way to compare galaxies, but it should not be mistaken for a wall that a spacecraft could cross. Nothing would flash on an instrument panel. The stars would not suddenly change. the gravitational pull would not drop to zero. A traveler would simply continue outward while the Milky Way's influence became weaker. This brings us back to escape velocity. At any chosen starting point, the escape condition asks whether the traveler has enough total energy to continue receding rather than eventually turn around. If it does, the trajectory is unbound. Once that condition is satisfied, the traveler does not need to reach a particular outer shell before escape becomes real. In the language of orbital mechanics, the decision has already been made by the trajectory. The remaining distance only determines how long the departure takes. That is why a hypervelocity star can already be described as escaping the Milky Way, while still physically inside its halo. Its journey may continue for millions of years through regions where galactic gravity remains measurable. But if its energy is sufficiently high, that gravity can slow the star without ever stopping and reversing it. The star is still within the galaxy's extended surroundings, yet it no longer belongs to the galaxy in the same gravitational sense as the Sun. This is the answer our journey has been approaching. There is no single true edge of the Milky Way that replaces the bright rim in a photograph. There are several useful edges depending on what is being measured. The stellar disk has one scale. The sparse halo of visible stars reaches farther. The dark matter halo reaches farther still, though its exact extent remains model-dependent. And gravitational escape is not an edge at all. It is a condition, a change from bound to unbound. So the question, how far must we travel to leave the Milky Way, does not have one clean distance as its answer. A better question is, what trajectory would allow us never to return? For Voyager, the answer is still no. For the Sun, the answer is no. For almost every star in the Milky Way, the answer will remain no throughout its life. But for a small number of stars thrown outward with enough energy, the answer is already yes, even while the long passage through the halo continues. The edge we were looking for was never a line in space. It was a statement about gravity. Far from the Sun, Voyager 1 continues along the same outward path it has followed for decades. Its signal is faint now. A command sent from Earth must cross an enormous distance before it reaches the spacecraft, and a reply must cross that same distance again before anyone here can receive it. Voyager is small enough to disappear against almost any image of the galaxy, yet it gave us a useful place to begin. At first, leaving seemed like a matter of traveling farther, past the planets, past the Sun's immediate surroundings, eventually perhaps past the bright stars themselves. But distance alone was never the answer. The Sun, Voyager, and nearly every star around us are already moving through space. What keeps them together is not stillness, and not a physical boundary. It is gravity. From very far away, the Milky Way might look much like the distant spiral galaxies we see through telescopes. A softly luminous disk, brighter toward its center, surrounded by darkness. The Sun would vanish into that light. Earth would be impossible to distinguish. Voyager would be smaller still, and even then, the image would show only part of what we had left behind. Around the luminous galaxy would remain the much larger structure we cannot photograph directly, revealed instead through the motions of stars and the bending of light. The Milky Way we see is therefore not quite the Milky Way we weigh. Its familiar glow marks where much of its ordinary matter shines. Its gravity reaches farther. That is why the question of escape led us outward through several different boundaries, without ever finding a final wall. The last bright region was not the edge. The last scattered halo star was not the edge. Even the outer scale assigned to the dark matter halo depends partly on how astronomers choose to describe a structure that fades gradually into its surroundings. For an escaping traveler, the decisive change happens earlier. A trajectory becomes unbound. Gravity continues to pull. The traveler continues to slow. but it never slows enough to turn around. And so a star can still be crossing the Milky Way's distant halo, while its future has already been decided. Voyager has a different future. It will continue far beyond the worlds it was built to visit, long after its instruments can no longer speak to Earth. But it will remain part of the galaxy's broader gravitational story. So will the Sun. They will continue moving through a structure whose brightest parts are easy to see and whose largest part is known mostly by what it does. And perhaps that is the quietest answer to the question we began with. To understand what it would take to leave the Milky Way, we first had to understand what the Milky Way actually is. Not only a spiral of stars, not a disk with a simple rim, but a vast gravitational system extending far beyond its visible light. The faint signal from Voyager is still traveling home through that system now, and around it, unseen but measurable, the galaxy continues to hold its shape.